Okay, guys. In the last lecture, we discussed about the Broglie hypothesis. The Broglie hypothesis. What it means is we already discussed that waves have dual nature. By dual nature, I mean sometimes a wave behave like a wave, or sometimes it's behave like a particle. And we already discussed in detail the wave nature of like diffraction of wave, diffraction, interference, polarization. Like diffraction, interference, and polarization, these are the wave property. But we also discuss photoelectric effect, Compton effect, and then we have pair production. These effect or these experiment tell us that electromagnetic wave like X-rays or gamma rays, etc., like electromagnetic wave behave like a particle. These are the particle nature of electromagnetic wave. Like electromagnetic wave, at a time electromagnetic wave behave like a particle as well as like a wave. So next, in 1924, de Broglie proposed that de Broglie extend the dual nature of electromagnetic wave to material particle. He says that if a wave behave like a wave, or if a wave has a dual nature, like it is a wave nature and particle nature, then according to this hypothesis or the Broglie hypothesis, a material particle has also dual nature. It behave both like a wave as well as a particle. Wave nature and particle nature. Now, we have no doubt about the particle nature of a particle. Like electron is a particle, it behaves like a particle. But how we can explain the wave nature of electron? This was given by de Broglie that a particle also behave a dual nature. Like the dual nature is universal. By universal I means if a wave behave like a wave nature as well as a particle nature, then a particle also behave both wave nature and particle nature. I can say that this dual nature is universal. We already discussed about it in detail in the classroom. And then de Broglie calculate the wavelength of this, calculate a relation between wavelength and momentum, which is given by this. Like this side of this equation, this side represent the wave nature, because wavelength is a property of wave, and on this side we have momentum, which is a particle nature, which represent the particle nature. So here we have a wave phenomena or wave nature. So they are related with each other by this constant, and this is called Planck constant. So next we have to discuss, because we already know that a particle is a particle, so we have to discuss about the wave nature of particle. But before going into the detail of wave nature of particle, for that we will discuss two experiments. One is called division and German experiment. Division and German experiment. And the second one is, I think the second experiment is J.P. Thomson experiment, I think. Yes, J.P. Thomson experiment. These two experiments prove the wave nature of electron like particle. So we will discuss these two experiments in detail in the next video. But here I will calculate the theoretical value of wavelength for electron. So for that I will start from my simple consideration, that consider an electron. Suppose we have an electron having mass m and charge E, and this electron is accelerated, which is accelerated through a potential difference, of, let's say, V volt. This is the voltage, okay? So V volt. And this electron is accelerated from rest to certain velocity. Like initially the electron was at rest. Once we will apply a potential difference somewhere in this region of V volt, then this electron will accelerate from rest to certain velocity, and it will move in this region. Now in this case, the work done on the electron is given by EV. This is a well-known relation. We already did it in electromagnetic course, electricity and magnetism. Now this is the work done in moving an electron from rest to certain velocity by applying a potential difference. Now this work done, I can write it here, this work done is equal to the kinetic energy of the electron. Or we can say that this work done is stored in the form of kinetic energy, which is given by K is equal to E V. Now we know that kinetic energy is half mv square, which is equal to E. This capital V represent the potential difference of voltage. From this, if I calculate the value of velocity, which is V, which will be equal to 2 EV over m square root. Let's say this is equation number 1. Now from de Broglie hypothesis, we know that the wavelength and momentum are related by this relation, lambda is equal to h over p. Here this represents the wavelength, this is the momentum, and this is the Planck constant. We can write it as like this: lambda is equal to h over momentum is mass time velocity. Now we already know that from equation 1 the value of velocity which is given here. If I put equation 1 and equation 2, then we have lambda is equal to h over m into square root of 2 EV over m. If I bring this m inside this square root, then we have lambda is equal to h over 2m EV square root. Now here I will use some values which I will explain later in J.P. Thomson experiment or division and Germer experiment. Suppose we have let the voltage we applied is, let's suppose, 45 volt, and we know that the Planck constant H is 6.626 into 10 raised to the power minus 34 joule second, and we know that the charge on electron is 1.6 into 10 raised to the power minus 19 coulomb, and we know that the mass of the electron is 9.11 into 10 raised to the power minus 31 kg. If I put all these values V, H, E and M in this equation, we get the value of lambda, which is 1.66 into 10 raised to the power minus 10 meter. We can say that lambda is equal to 1.66 angstrom, because 10 raised to the power minus 10 meter is equal to 1 angstrom. Now this represents the theoretical value of wavelength. This is the theoretical value of wavelength. Now there is another experiment which I am not going into the detail, but I will just write the value of wavelength from that experiment. And we know that the wavelength of X-ray diffracted by reflecting planes. Like here I will write the statement is the wavelength of X-rays diffracted by reflecting planes is also 1.67 angstrom. Like if we diffract X-rays from atomic plane, suppose we have an X-rays, okay, here we have a material, these are the atomic sites, these are the atoms inside the material, this is the crystal structure. Okay, if we fall X-rays on this atomic plane, then these X-rays diffracted in different directions. Okay, so the wavelength of these diffracted X-rays is 1.67 angstrom. Now we know that X-rays is a wave, and this is the wavelength of electron, and we know that both the wavelengths, they resemble with each other, because the wavelength of electron is 1.66 angstrom and the wavelength of diffracted X-rays is 1.67 angstrom. They are almost equal. Now X-rays is a wave, and we know that the electron is a particle, but here we have the wavelength of the electron is given by this, so it means that electron behave like a wave. if we compare both the wavelengths are the same, so it means that X-rays and electron, they behave the same. So this is what we call it, the theoretical value of the theoretical calculation or the theoretical value of wavelength for electron. And from this theoretical calculation and also from this experimental fact, we see that electron also behave like a wave. But we will later in the next video, if I discuss the division and German experiment or J.P. Thomson experiment, in that experiment you will clearly we will clear this phenomena that electrons also behave like a wave. Electron also behave like a wave. So which we will do in the next video. Thank you.